Peter made this suggestion that we could hold online seminars using some of the facilities that OSU has. And I think it's a great idea. So let's see how this goes. I mean, if we're going to be doing climate research, we need to think about how to collaborate in environmentally friendly ways. And so I'm hopeful that this will be successful. Please send to Peter and I your feedback on how this works and whether there's something different we could do in the future. And so I hope everyone can hear me. If you can't, type something into the chat box saying that there's a problem. And no, it's okay. So I'm going to be talking about two different projects that have clear Statmos connections, but are also part of another NSF center called RIDCEP. So let me say a little bit about that. Why am I not being able to page it? Okay, so this research is funded by both RIDCEP and Statmos. There's a list of my collaborators, some of whom are online here. So let me tell you a little bit about RIDCEP, and maybe I'll say more about Statmos at the end. All right, so page down. Okay, so RIDCEP's also funded by NSF, and RIDCEP stands for Robust Decision Making for Climate and Energy Policy. And those 4 bullets there are the kind of the 4 main goals of the center. I don't really have anything to do with the first, and maybe something to do with the second and fourth. I'm not really involved on the policy side, more on the climate side. So that is, if you're going to make statements about what kind of climate and energy policies we're going to have in the future, you need to know something about how the climate is going to change and how that's going to impact economies. So what the economists need then, in some sense, to run the kind of models they use is they need to be able to quickly say, if we've got a certain scenario for greenhouse gas emissions, what's the climate going to be like? And they can't stop, and every time they want to look at a new scenario of emissions to rerun some massive climate model. I mean, they basically want answers almost instantaneously. And furthermore, depending on the impact they're looking at, so I think the easiest one to think about is agriculture. For agriculture, you would ideally like quite highly resolved in both space and time climate inputs. That is, global averages aren't that interesting. Annual averages are not all that relevant. And so that is kind of what we're aiming at, being able to produce future climates at maybe about the daily scale at a fairly high spatial resolution. Now, in principle, you can use GCMs for future climates, although that's a mistake, as I'll talk about. But you can't do it quickly. I mean, the GCMs are just slow, and so we need to think about an alternative ways of doing that. So, okay, there's basically 2 things I'm going to talk about here. So the first part is climate model emulation. So emulation of computer models has been going on for about 30 years now. And the basic idea is you have some computer model with some outputs of interest, and outputs I'll label by O, and inputs I will label by I. And now let's suppose you can afford to run the computer model, but only a limited number of times. So as computer model emulation was originally thought of, so N was the number of computer model runs you could do. The original thought was that N could be fairly large, and so that you'd have pairs of outputs I1, O1 through IN, ON, but not as large as you'd like it to be. And therefore, what you'd like to be able to do based on that training set of N runs is to figure out a statistical surrogate or emulator that, given some new set of inputs I knew, would allow you to very quickly say what the output would have been without having to run the computer model over again. Now, with climate models, it's always going to be the case, no matter how big and fast our computers are, that the best climate models can only be run a very limited number of times, because you can always increase the resolution, you can always add more processes. And so there's no sense in which, if we wait, we'll be able to run our computer model lots of times. Like, the computer models will just change as the computers change. And so therefore, we'd like to be able to maybe do climate model emulation with very few runs, perhaps only one. And so that may seem absurd, right? How can you learn outputs from inputs when you only have one example of when n equals 1, basically, or 2 or 3? Well, the reason it can be done is because we don't have a generic problem here. We have a specific problem here. So let me explain the setting and why it is that we might be able to do emulation with a very small number of runs. So some notation. So I'm going to mostly focus on temperature, although I'll talk about precipitation a little bit. But capital T of T be the temperature, and the first part of the talk is only about the annual level. I'll look at the daily level in the second part. So T of T is the temperature in year T. And let's suppose for now we're just looking at a specific region. So we're only just looking at, so T of T is just a single number. And then CO2 of T is the concentration of CO2 in year T. And so our inputs here are going to be the CO2 concentrations. You could argue that really the inputs to the model should be the CO2 emissions, but then you would need a carbon model. And so we're going to assume that what we know is the CO2 concentrations. And now, so what is the temperature a function of? So the temperature in year T is in principle a function of the past trajectory of all the forcings, of which we're only focusing on the CO2 here, plus the initial conditions for the model. So these GCMs are deterministic models. There's a sense in which the temperature at a certain pixel is a function of the inputs, which are the past trajectory of CO2 plus initial conditions. Now, the thing of it is we run our models, so I am assuming we can run our models for a large number of years. So one run gives you not just one piece of information about that relationship between inputs and outputs, but a lot of pairs of points. So that is, we have for the year 2016, we have the past trajectory and the temperature. For the year 2017, we have the past trajectory and the temperature. And we can use all of those pairs to develop an emulator. So that is the model that I'm going to have in mind, and even this model makes, in some sense, quite a few assumptions, is that the temperature at year T is some function of the past trajectory of carbon levels plus some remainder term. And that remainder term I'm going to treat as stochastic, and that's going to basically to take care of initial condition uncertainty. And there's good reasons for treating the initial condition uncertainty as stochastic, although that doesn't mean that it should be an additive effect with mean zero, but I don't think that's too bad an assumption. Because the important part about this relationship here, I'm trying to highlight, I hope you can see the hand, is that function f doesn't depend on t. It's the same rule. You don't need one rule for predicting temperature in 2030 and another rule for predicting temperature in 2040 and another rule for in 2050, which is how you might view the problem if you viewed it as a generic problem in computer model emulation where you had a bunch of inputs and a bunch of outputs. Our outputs are all related to each other, and they're all related to the inputs in a very structured way. Okay, so that's the basic idea. So what did we actually do? Well, not we in this case means not me, some of my collaborators made a very large effort to create a set of 25 runs of one of the newer but no longer cutting edge climate model, CCSM3. It's been replaced by another model at 96 by 48 horizontal resolution, which is now considered low resolution, although 20 years ago would have been considered pretty cutting edge. But we needed to keep the resolution down because we didn't have infinite computer resources and we wanted to do a lot of runs. There are 25 total runs, and they are made up of 5 carbon dioxide scenarios, which I'll show you in a moment, each run 5 times. So the difference between the 5 runs are in the initial conditions. And we're going to treat each of those 5 runs as basically independent replicates of the same process. Okay. And then what we're going to try to do in this first part of the talk, we're going to mostly focus on emulating the mean, so mean over initial conditions of the temperature trajectory for a given CO2 scenario. All right. And we're going to take advantage of the fact that we have these multiple runs of each scenario to give us replicates so that we can actually do simple statistical operations to decide how well we're doing. So here's the 5 scenarios, and they have names that are hopefully evocative. Slow is 1, a slow ramp up, and we're going to top out at 700 ppm. So pre-industrial CO2 is about 280, and so 1 says we're going to slow down things, but we're still going to stop increasing at 700. 2 is a moderate that stops at 700. 3 is a fast that stops at 700. 4 has a sudden jump up to 700. 5 has us going up to like 1200, and then the miracle occurs and CO2 goes back instantly to pre-industrial levels. The runs with the jump up and the drop are to help us try to learn something about short versus long-term effects of changing CO2. Okay, so what's our model for the emulator? So it's actually going to be very simple. It's not going to be some elaborate Gaussian process model with non-parametric formulation. It's actually a parametric model that uses something of what we know. So there's good reason to believe that the relationship between temperature and CO2 is going to be related to the logarithms of CO2, that temperature increases should be roughly linear in logarithms of CO2. So there's a couple, so beta naught is basically the baseline temperature, so pre-industrial temperature. Beta 1 times this term here, so this is kind of the short-term effect. It could have put other things here, but given the temperature, everything's only be recorded at the annual level, it's hard to distinguish between various forms of the short-term effect. And then beta 2 refers to the long-term effect. So these WIs you see down here, basically a geometric series. So where this coefficient rho describes how the coefficients decay. So the closer rho is to 1, the more the past matters, and the larger rho is, the less the past matters. So we're going to basically fit this model regionally. And the kind of things we should expect is, for example, but I'm not going to look at this much here, is that rho is probably bigger over water than versus land. That is, the past matters more when you're over water versus land. And then the error term we're just going to model as an AR1 term. And this model, we're going to do it region by region, and I'll show you the regions in a moment. Okay, so that's a pretty simple model, and it's easy to fit. And let's see how it does. Okay, so here's so before I show you the results, we also are emulating precipitation, and here's something that we came up with. I don't love it, but it seems to work okay. We're just going to say that the precipitation emulator is linear in the temperature emulator. So this T hat is the temperature emulator that I just came up with, plus an additional short-term effect in log CO2. And it's hard to find, at the annual level, it's hard to see much evidence for correlation in the remainder term for precipitation, so that's just white noise. Okay, so now I'm going to show you some actual results for a couple of scenarios and a couple of regions. Okay, so the two regions that I'm showing results for are temperature emulation for the North Pacific West and precipitation emulation for the Eastern Pacific West. Okay, so the red curve is so what is the emulator trained on? It's trained on just two runs. So in some sense, so N is 2 here. One fast realization and one jump realization. And we are emulating for, on the left-hand side, the slow scenario, and on the right-hand side, the drop scenario. So here we're just emulating the mean. So here's the mean emulator, and then the gray is the 5 realizations of the slow scenario superimposed. And, you know, the red curve basically goes right through the middle of these gray curves. So at least in terms of emulating the mean temperature, our emulator looks basically perfect for this region. For precipitation, of course, so these are precipitation anomalies. You know, of course, precipitation is much noisier than temperature, but again, the red curve seems to go very nearly through the middle of these things. So at least in terms of emulating the mean, we seem to be doing about as well as we can do. The right panels show what happens when we try to emulate for the drop scenario. So the drop scenario is very different, is an extreme scenario. It's totally unrealistic. It's not something that we would care to emulate for policy purposes. And it's extremely different than the training sets, which included one fast and then one jump, where the jump is a jump upward, but not nearly as big as the drop downward. Even here, it's not terrible. You can definitely see a little bit of misfit there and there, but it's not awful. It's not awful. The precipitation is pretty good. There's this jump up here, which is actually apparently physically plausible. That is, so in general, in most places, the higher the temperature, the more the precipitation, right? The warmer temperatures are, the more evaporation you get. So you tend to get more total precipitation, although that's not globally true. But apparently there's good reason to believe that the initial effect of suddenly dropping CO2 will be to increase precipitation. And maybe that's, well, maybe I won't speculate. There's probably people listening who could offer better explanations than I could. Okay, so I would say that in terms of the mean emulation, that we're doing pretty well. This next slide has to do with trying to actually emulate the annual temperatures and precipitations themselves. And all we've done here is we've added the AR1 process and for temperature and the white noise process for precipitation onto our mean emulator, and then shifted them. So gray is the data, the red is the emulated one. It's only off because we've shifted it for visibility. In fact, again, it would be really hard to tell the difference between what actually came out of the model and what our emulator produced. Here's the same thing for precipitation. And again, at least in these pixels, you would be really hard pressed to tell the difference between the emulator and the model output. Okay, so that just showed you a couple pixels though. We like to show you how we can maybe evaluate things in a more global way. And so we're going to take advantage of the fact that we basically have what we consider to be essentially 5 IID realizations of each scenario. And that allows us to give an estimate of the best our emulator can do. So this denominator is an unbiased estimate of what the perfect emulator would do, because it just replaces the expected value of TR by the average over the 5 realizations, and then, that's just the usual correction. And then the numerator is how well our emulator is doing. So N1, so if our emulator is perfect, N1 and O1 should have the same expected value, and therefore I1 should be near 1 if we're doing well. It might be slightly less or slightly greater than 1 just because of random variation, but it should be near 1 if we're doing perfectly and somewhat bigger than 1 if we're not. I2 is a measure of, oh, you can't see the pointer. All right. Okay, I will try not to refer to the pointer. Something to work on for the next, next effort. So I2, most of the way down the page, this is a measure of how much variation there is to explain. So small values of I2 means that there's hardly any change in the quantity you're looking at, and therefore there's no point trying to explain the trend. And I2 large means that there is quite a bit of change in the mean relative to the variation in the process. Okay, so here's for this, again, training on a single fast and a single jump scenario. This is the big numbers are the I1 values times 100. So 100 basically means as good as you can expect. And you can see that, and the small numbers down below are the I2 values. And you can see that most of these numbers are very near 100. You can see the only one that's quite a bit bigger than 100 is down here in the Southern Ocean. And there's reasons that the Southern Ocean is hard to emulate, probably having to do with issues doing the sea ice. And anyways, no one lives down there, so it's not that important. But you can basically see that globally, the emulator is doing basically perfectly in terms of mean emulation of annual temperature at the regional level. Here's for the drop scenario, which is, of course, much harder. Of course, now these I1s are quite a bit bigger, but you can see that, in a lot of places, it's not much bigger than 100, especially, not surprisingly, for a lot of these things over populated, developed world areas. Models tend to do better there. But I still consider these numbers pretty good, given this is a completely unrealistic and drastic extrapolation from our training set. So I view this as saying that the mean emulation is basically fine. Okay, so what about how much of a training set we need? So these are these I1s. These are basically box and whisker plots for the I1 values. Here, so if you look at the left panel, slow means training just with one slow scenario. So with n equals 1, these are the I1 values. You can see that most of them are less than 1.1. In fact, more than half of them are less than 1.05. And even the biggest one is only about 1.2 something. If we add to that slow scenario the fast, so now we have n is 2, a slow and a fast scenario, things get noticeably better. If we add the jump scenario to our training set, things don't maybe get a tiny bit better. And now if we add the drop scenario, things actually get worse. So this is a sign that our model, our emulator model, isn't really perfect, that those betas are not really the same for every scenario. And if we stick in the drop scenario, which is very different from the scenario we're trying to emulate, which is the moderate scenario, we can actually make things worse. So there is some sense in which the training set, the elements of the training set shouldn't look that different from the elements from what you're trying to actually predict if you want a good emulator, and that's not surprising. The right-hand panel just uses the fast scenario and then adds realizations. So 1 on the left, 2, 3, 4, 5. You can see again, 1 is already quite good, 2 is better, 3 is the tiniest bit better, but once you're to 3, going to 4 and 5 hardly helps at all. So again, we can do mean emulation of temperature for reasonable scenarios with tiny training sets. Okay, so that's some summary of some of the main findings. This paper has just appeared, the paper on this work just appeared in Journal of Climate. There's other things we did. So the other way that people might try for avoiding running climate models repeatedly is what's called pattern scaling. I don't really want to go into it, but it's very simple. Our methods generally did better than pattern scaling, even though we allowed pattern scaling to cheat in some sense, that is to peek at the results from our emulator in some sense. But pattern scaling in some circumstances isn't too bad. It's not, you know, for scenarios where things don't change that much, it's not bad a method. So these showed you predictions at the regional level. We would actually be interested in, for many cases, for emulation at finer resolution, and we have some methods for doing that, although I think we can do better. Notice that I was doing everything pixel by pixel, so we're not taking any account of spatial dependence in our stochastic component. I do have a paper with Stefano, who's apparently listening in, where he did a lot of modeling of the space-time, developing a space-time statistical model for computer model output, so we could try to get the space-time part right. But let me point to the next part of the talk, which I think has a different and perhaps better way of dealing with these things. We also ignored dependence between temperature and precipitation, which we're now aware of is not appropriate. I mean, it doesn't affect the mean emulator, but if you wanted to do simultaneous emulation of temperature and precipitation, at least in some places, there can be quite a strong correlation between annual temperature and annual precipitation, and you want to take that into account. We just treated the model as given. There's no accounting for model uncertainty. It's possible in principle extent we've done to that circumstance, but we don't have yet the model runs to do that. There are people who have looked at that issue. We have started to look at other, so this is just one GCM. We have looked at some others, and the emulator seems to work okay. There's clearly more, though, we can do just on this level. But I'd like to talk about something else, because, you know, it's one thing to emulate a computer model, and that's nice that we don't have to keep running computer models over and over, these big GCMs over and over again, but really we're much more interested in the future climate, not what the climate model says the future climate's going to be, and those, of course, aren't the same. So, so we've been thinking about this for a while, and I'd like to try to push some principles here for thinking of, so not just some specific methods, but some principles for how to think about this. So here's a principle that I hope people can remember, that this will actually, by kind of formulating these principles, that we can maybe affect the debate. I think if you give people short things to remember, then maybe it makes it harder for them to ignore what we're doing. So here's the do no harm principle of climate model emulation. So if you think some characteristic of climate will not change in the future, then your simulator should reproduce the observed patterns for that characteristic. Right? Why change what we've observed if you don't think they're going to change? So let's think about two simple ways of possibly doing future climate simulation, and both of these are things that are done. So let's suppose we think that it's only the means of climate that's going to change. So nothing else about climate is going to change except for means of whatever you're interested in. So two ways you could then try to simulate for future climate is you could take future climate model output and then say, well, we know climate models are biased, so let's take the future climate model output and shift it by the difference between the computer model output for the present and the data. Okay, I would say that does not satisfy this principle of do no harm, because to the extent that the model output does not match the variations in the present climate, and it definitely doesn't, then this will not respect the variation in the observations. On the other hand, if you start with the observations and use the difference between the means in the future and the present GCM, this is what would be called the delta method, this does satisfy this principle because it only shifts the means in the observational record and nothing else. Okay, so if only the means were going to change, then the delta method would be a good way for simulating future climate. But surely more than the means will change, although maybe that's a good question to be thinking about. To what extent will things other than the means actually change? So let's suppose that it does. And let's suppose, for example, that the variability will also be different in the future. All right, so we need some notation. So let's let Z naught T be the observed. And so now I want to work at the daily level because that's more interesting. But I'm only do temperature. Precipitation at the daily level is obviously extremely challenging. So let's just do temperature at the daily level. So let's Z naught T be the observed daily temperature at some location and time T, for T from 1 to capital T. And let's let mu naught of T and sigma naught of T be the standard deviation of this series. And so both of those might depend on T. So we're not assuming that the process is stationary in either its mean or its variability. And now what we want to simulate is some new process, Z1 of T. And suppose we know its mean and standard deviation. Then a way we could simulate Z1 of T without actually producing any random numbers is take the observed series, so look the displayed equation most of the way down the screen, Z naught of T, subtract its mean, multiply by the ratio standard deviations, and add the new mean. So this will create a new series whose mean is mu1 of T, what you want, and whose marginal standard deviations are sigma 1 of T. So in some sense, it'll correct the means and standard deviations of the observed data record. Okay, so is this actually adequate? Well, I would argue that it's not completely adequate. And one way to see this is, well, we could do this same operation at different timescales. So for example, we could do this transformation on the daily scale, and then we could do it at the annual scale, and then we could ask, if we aggregate our daily scale simulation to the annual scale, will we reproduce what we would have gotten when we did the transformation directly at the annual scale? And the answer to that is no in general, because the way we've done things takes no account of temporal correlation. And in particular, if temporal correlation is going to be different in the future than the present, this methodology will not be aggregation consistent, or whatever you want to call it. So really what we want to do is not think about modifying the distribution of one quantity at a time. We want to think about modifying a whole multivariate distribution. So Z naught of T as a vector for different T's, we want to modify the distribution of that into the distribution of Z1 of T. So that's really hard. I mean, how do you think about modifying, one maybe 100-dimensional distribution into another 100-dimensional distribution? And what if, furthermore, we think about it as a space-time process, and so now we have, so even with a crude model at the daily scale over 100 years, we have, Z naught. The Z naught could be, easily a million things. So how do we modify a 1,000,000-dimensional distribution to another 1,000,000-dimensional distribution? Well, that seems to be very hard. And what I would argue is that maybe it's better to first transform the observations, and a natural thing to do is to do this in the frequency domain. Okay, so why does moving to the frequency domain help? Well, one argument is to use this really amazing result about stationary time series. So maybe we don't have a stationary time series, but in this case, something really amazing happens. So under some regularity conditions, you take the discrete Fourier transform of a stationary time series, then that's a transformation to approximate independence and normality. Okay, so that is you get something, the output, even if the original series is not exactly multivariate normal, the actual DFT, because of a central limit theorem effect, at least at a finite number of frequencies, is very nearly multivariate normal. It has mean 0 except for the 0 frequency. That's an exact result. It's not approximate. The components of the DFT are almost independent of each other. That is, their covariance matrix is nearly diagonal. And furthermore, the variances of the components of this DFT are very nearly equal to the spectral density at the corresponding frequency of the discrete Fourier transform. All right, so that is, we have, without having to know F, we can take a transformation of the observations that will nearly be to independence. And it's much easier to think about transforming distributions of independent components than of highly dependent in some complex way. So we're going to transform to the frequency domain, and then we're going to reweight the variability of things, and then we're going to transform back. So let's suppose G0 is the spectral density under current conditions, and G1 is the spectral density under future conditions. Let's suppose for now we know those two spectral densities. And then Wj is just the jth Fourier frequency. Then this displayed equation is the basic idea. We first have to subtract off the mean of Z0 of t. Then we take the discrete Fourier transform. Okay, and then there's this ratio of square roots. That reweights the variability at different frequencies. And so that's the kind of the main step here. Then we do the inverse discrete Fourier transform. Then what this is going to do is this going to produce, at least approximately, a realization of a stochastic process of length t that has the mean we want, mu1 of t, and the spectral density we want, G1. Okay? So that's the basic idea. Now there's a lot of details that we have to think about. Okay, so where are all these things going to come from? Well, the mu naught, the things with knots in them, presumably we can at least in principle try to estimate from the data, although those are things that we need to think about. But what about the things, the mu1 and G1? So these are statements about the future. Where are we going to get those from? All right, well, we don't know the future mean and spectral density, but we do have present and future computer model output. So I want to distinguish between means and spectral densities for reality versus model output. So let's let nu naught and nu 1 be the means for the model output for the present and the future. So the delta method basically assumes that the model gets these differences right. So that first displayed equation, we're going to assume that nu 1 minus nu naught is approximately mu 1 minus mu naught. All right, so mu naught and nu naught may not be so similar, and mu 1 and nu 1 may not be so similar, but what we're hoping is that those differences are similar. And there's at least some reason to believe that's not such a silly assumption. And we're going to do the same thing for the spectral densities now. So G1 over G0 is what we want, and we're going to hope that it's well approximated by F1 over F0. So the ratio of spectral densities for model output, we're hoping is close to the ratio of spectral densities for reality. Okay, so once we can estimate that difference in mean and that ratio of spectral densities, then we can go ahead and apply the algorithm on the previous slide. So one interesting statistical point that the last bullet here on this slide shows is that we really are only interested in this ratio of spectral densities, not the individual spectral densities. And that suggests a little bit of an interesting statistical point, because that ratio of spectral densities is very likely to be close to flat. Because unless we do a really radical change to the climate, we don't expect the spectrum to change that much. And therefore, so when you estimate spectral densities, you usually have to make some assumption about smoothness. So the smoother something is, the flatter something is, the more you can smooth it and the better an estimate you can get of it. So we advocate just estimating that ratio, log of F1 over F0, rather than F1 and F0 separately. And we put a penalty on that ratio. And so that's maybe the kind of the interesting statistical point here. All right. Okay, so let's see. I basically have said all of this already. This is just a little bit more notation to point out that this algorithm can be viewed, so here's leaving out the mean, so it's not so complex, can be viewed as just a bunch of matrix multiplication. So D is the discrete Fourier transform matrix, that's a known matrix. M is this diagonal matrix that's based on this ratio of spectral densities. And so what do we see? So the do no harm principle, so the last bullet on this slide, says this M equals I. So if we think the variability in the future is not going to be different from the present, then d inverse n dz is just z. We just reproduce the data. So this is an example of do no harm. So I'm going to show you some examples for a simple process, just a process in time with an exponential covariance function and all the means 0. I'm going to show you how the actual process is modified depending on the values for m. Okay, so the first case here, so look at the lower plot. The lower plot just shows us that we're basically saying the power is going to be cut in half at all frequencies. This is exactly the same as just multiplying the process by a half. So in every case, the black process, the black curve in the top figure, is the simulated process, and the red curve is what happens when we take the discrete Fourier transform, multiply by this M matrix, and then take the inverse discrete Fourier transform. So all the red curve here is 1/2 times the black curve, and you can see that both small scale and large scale variations have been suppressed doing this. So, okay, no surprise. Okay, now look at the bottom curve here. Here we can see that low frequency variations are being suppressed quite a bit, whereas high frequency variations are being hardly suppressed at all. So now look at the top plot, and you can see that that's what's going on. You know, in terms of the local fluctuations, the red curve and the black curve look very similar, but in terms of the larger scale fluctuations, the red curve has much less large scale fluctuations and therefore much less overall variability, even though the short scale variability is very similar. Okay, the next page shows the reverse. Now we have very little suppression at low frequencies, but substantial suppression at high frequencies. And what we get is the red curve is just basically a smooth version of the black curve, which is what you expect. This is basically a low pass, what engineers and electrical engineers would call a low pass filter. And so it just smooths out the black curve. Okay, so the final one's the most interesting. Here we have suppression at low frequencies and amplification at high frequencies. So now you look at the red curve, and you see in terms of overall variation, it looks like it's less than the black curve. But in terms of the local variation, if you look carefully, you can actually see that some of the local variations are bigger in the red curve than in the black curve. So you can have this, you know, less power at some frequencies and more power at others. Okay, so that's where the input process is a stationary Gaussian process. What if it's not a stationary Gaussian process? So to give you some idea of what's going on. So my hope here is that even though the simple theory really works best if the process is stationary and Gaussian, that because of the do no harm principle of this algorithm, that if the process is not stationary and Gaussian, it still won't be such a bad idea. So I'm going to look at what this algorithm does if I exponentiate the previous process. So that'll be the first example. And the second example will be what happens if I add more variation in some seasons than others. Okay. Okay, so the black curve is just the exponential of the previous black curves. When you exponentiate a Gaussian process, what you're going to get is greater variation where the levels are higher. Okay, and so now I applied this. So I just took that process. I didn't assume I knew it was. I just took that black curve. I took its discrete Fourier transform. I multiplied by the M matrix implied by the curve on the bottom, and I took the inverse discrete Fourier transform, and that's where I get the red curve. And you can see that in part it retains some of the non-Gaussian features of the black curve, in the sense that the local variation is larger where the levels are larger. So even though there was nothing about this procedure that recognized that the process was non-Gaussian, because it was driven by the black curve, it reproduces at least some of the non-Gaussian aspects of the black curve. Okay, so now I have a, so if you look at the black curve on this page, if you look carefully, you can see there's more variation at the beginning of the process, and in the middle of the process, and at the end. So I basically multiplied the black curve by a function that was big near 0, was big near 125, and big near 250. I took that process, which is just not a stationary process anymore, but I ignored that. I just threw it into my algorithm anyways. I took the discrete Fourier transform, I multiplied it by the M matrix implied by the bottom picture, and I took the inverse discrete Fourier transform and got the red curve. You see again that the red curve mimics some of the fact that the variability is bigger at the beginning and the middle and the end, even though my algorithm didn't know that. right? So again, because it's data-driven, it will tend to mimic characteristics in the data, even if it doesn't know that those characteristics are there. So this is a property, this is a consequence of this do no harm principle. Okay, so this is still pretty limited, even though I think it's in some ways a pretty big step forward. So there's one issue that, there's many things you could object to, but there's one issue that we kind of know how to deal with, so I want to say something about that. And that is that temperature on a daily level, even if you take the mean out of the seasonal cycle, is still clearly, in most places in the world, at least certainly away from the equator, is clearly not a stationary process. That is, if you think about it, almost anywhere you live, there is more variability in temperature in the wintertime than the summertime. So for example, in Chicago, in January, the highest temperature in January of all time, I think, is about 70 Fahrenheit, and the lowest is 27. So basically about a 100-degree spread. Whereas the highest temperature in July, I think, is 105, and the lowest is maybe about 50. So about a 55-degree spread. So there's just, and if you think about it, wherever you live, there tends to be much less variation in summer than winter, and there's good reasons for the physical reasons for that. So first of all, you might say, hey, I just showed that ignoring a seasonal cycle wasn't so bad. So maybe we can get away with ignoring it, but we did come up with a way of dealing with it, so I want to say something about that. So let's look at some data. So our data here is not actually raw station data. It's what's called reanalysis data, and I don't want to go into what that is, but it's largely data-driven, and it's a gridded data product. So we have data, we have present model output from our CCSM3 run that's based on a long baseline pre-industrial CO2 level run. And then our future model is the end of a very long run where we ramp, one of those runs where we ramped up to 700 ppm. So all I'm talking about is comparing two at least approximately equilibrium scenarios. And maybe I'll say a little bit more about that, because that's not really, we're not in an equilibrium climate right now. So all I'm talking about right now is simulating equilibrium climate. It's not actually the question of greatest interest for the next 100 years. All right, so I'm going to show you results from mostly from 3 pixels. The green X is basically Illinois. The red X is off the Gulf of Guinea in Africa, and the blue X is in the Southern Ocean. And here's 3 years of reanalysis data for those 3 places. Obviously, the red curve is Guinea, much warmer, much smaller seasonal cycle. Illinois, a huge seasonal cycle, much more high-frequency variation. And then the Southern Ocean, where you can see very clearly more variation during some times, more local variation during some times of the year rather than others. Like the wiggles in the blue curve clearly has a seasonal component to it. So it's very obviously not a stationary process in the variability, not just in the mean. Okay, but what we seem to have found is that even though the process is clearly not stationary, that the non-stationarity seems to be well approximated by a very simple form. And so our evidence for that is by giving these pictures here. So these pictures show seasonal spectra. So for each 3-month period, you compute a periodogram, you average those periodograms over however many years of data we have, and then we plot those 4 seasonal periodograms. Okay, so the reanalysis data is on the left, and what you can see is that red, so that's June, July, August, there's the least variation in summer and the most in the winter. So that's the blue, December, January, February. So like I said, less variation in summer and more in the winter. These are log spectral densities, and you can see that the 4 curves, both for the computer model output and for the reanalysis data, are not that, pretty close to parallel. Maybe a little bit of weird things happening at the lowest frequency. They're pretty close to parallel. And what does that mean? That means the different spectra, because those are pictures on the log scale, are pretty much multiples of each other. And that suggests that simple seasonal rescaling may remove most of the lack of stationarity in the process. So we're going to add one more term to our model. So this S0 inverse is an S1. So S0 is just a diagonal matrix that's a seasonal rescaling for the present observations. And then S1 inverse S0 is the change in seasonal rescaling. again, rather than trying to estimate S1, we're only going to use the model output. So if you go to the middle bullet down the page, we're only going to use the model output to estimate S1 inverse times S0, not separately estimate S1 and S0. So we're only using the model to say something about changes. So we're not using the model to say what the changes in seasonal variation will be, what the variations across seasons will be. We're only using the model output to say how that seasonal variability might be different in the future versus the present. So again, it's more of this do no harm principle. All right, so if we do this rescaling to the data and then do the seasonal spectra, you see the seasonal spectra lie almost on top of each other, which suggests that this rescaling is very nearly transforms us to a stationary process, ignoring the seasonal cycle and the mean, which we have to deal with in some other way. All right, so here's, for those 3 pixels I was showing you, here's our estimates, and they're pretty stable, of the ratios of the spectral densities. So for the Southern Ocean, what you see is that you have a very large suppression of variation that seems to be essentially constant over all frequencies. For Illinois, you see that there's suppression at all frequencies and perhaps a hint, so that's the green curve, perhaps a hint of more suppression at high frequencies than at low frequencies. And then at Gulf of Guinea, you get the interesting effect of it appears there's some suppression at low frequencies and then some amplification at high frequencies. Okay, so if we apply our algorithm, so here's just a little bit of an attempt to show you something about what happens globally. These are just 2 frequencies. These are the ratios of these estimated spectral densities. So blue means that that this model, CCSM3, thinks there'll be less variation in the future, and red means more variation in the future. So part of what you see here is that most of these maps are blue. There's a little bit of red at some places, but at most frequencies and most locations, CCSM3 thinks there'll be less variation in the future rather than more. Okay, so that's pretty important and pretty interesting, because if you asked a typical educated layman about whether climate change is going to create more or less variability in the future, I think most people would say, oh, more, because that's, if you read various articles about how we're going to have, more catastrophes in the future, those articles tend to suggest that there's going to be more variation in the future. But it's not clear that that's true, and at least CCSM3 thinks there'll be less variation in temperature in the future versus the present. And to me, that actually seems to be the 0th order physics, right? If you put a thicker blanket over the Earth, that should lower variability, not increase it. Of course, this is just a result for CCSM3. We've recently gotten similar data for another computer model, GIS. And for that model, it agrees over water that variability will mostly go down, but it seems to think in most locations that variability will go up over land. So part of what we have to be careful about is that different models are not necessarily going to agree about these changes in variability. So here are the simulated results for these 3 pixels. So blue is present and red is future. So the first 2 sites, it's hard to see much beyond the mean shift. If you look carefully, you could see that the variability was suppressed a little bit at Illinois. The interesting one, even though I don't believe it, is down here, where you see there's quite a bit of a different seasonal cycle in both the mean and the variability in the future versus the present. Notice, though, that these changes in mean temperature are enormous. Like in this season here, I don't know, that's like a 15 degrees Celsius change in temperature, which is probably not too plausible, although you have to be careful. So if you're in a place where there's sea ice and your model thinks you're going to melt the sea ice in the future, that you can get enormous changes in temperature, right? Because the presence of sea ice kind of keeps the temperature from getting too warm. And once you melt that sea ice, you allow for potentially a large warm up. So it's not completely absurd, although I think probably most people would look at that and say they don't really think the Southern Ocean is going to warm 15 degrees under 15 degrees Celsius under this scenario. All right, so there's lots of things we haven't dealt with. I've ignored spatial dependence, although again, in terms of our do no harm principle, this method will tend to mimic whatever spatial dependence exists in the data record. So we can use this method pixel by pixel, and we won't be producing future climates that say different pixels are independent, because the data will have dependence in them. There's also an issue of that reanalysis 2 data, which is the only really good global data product that exists, only goes back to 1979, and we might want to do simulations longer than 35 years. I think perhaps the biggest issue is this third one, is that we're not presently in a stationary climate, so what I've just shown you is not that helpful for the next 100 or even maybe 1,000 years. And there's also issues that I was really only changing means and variabilities, and it's certainly possible that shapes of distributions will be different in the future. So here's just a little bit of a model output. I'll try to wrap up in a minute here. So the solid curve is what these are marginal distributions by season at those 3 pixels. And then the dashed curves are modeled. For the blue is for the base scenario, which is not quite the present, it's pre-industrial. And then the red is what the model thinks is going to happen in the future. So basically it's 700 ppm. You'll note there's some pretty weird things, like here's what the model thinks for the present in the Southern Ocean. So if you look at the bottom row, the June, July, August, so the winter in the Southern Hemisphere. So you can see the blue dashed curve and the red dashed curve are very different in means, but that they're actually different in skewnesses, right? One of the blue curve is slightly skewed right, and the red curve is slightly skewed left. If that's actually true, then our method isn't really directly dealing with that. I'm not sure I believe it. There's also some issues that it looks like there's maybe something weird happening when temperatures are near zero. And that's not so strange. I mean, zero is the freezing point of water, and so it's not strange that there might be little humps in distributions near 0 degrees. So these are some things that not just our method, but no method that I'm aware of that's being used could really deal with. Okay, so we're starting to think about how to deal with transient climates, and that Andy Popik, who's listening or is at least logged in, is starting to work on that. It'd be interesting to think about combining the first and the second half parts of the talk. So what if we wanted to simulate a future climate for which we have no GCM runs? Then we need to combine this second half with an emulator from the first half. I think that would be interesting. You know, for ag models, people need precipitation at perhaps the daily level. What I'm suggesting here cannot just be carried over, because precipitation in most days in most locations is 0. And so these kind of linear approaches that I'm talking about are really not going to be suitable. Of course, again, it's not good enough to just do temperature and precipitation separately. We'd like them to do them together. And finally, suppose there were changes in spatial dependence, we would want to think of an extension of what I talked about here that would handle that. So those are just some of the very hard challenges that people who are involved in Statmos might want to be engaged in. Here's some final questions that I'll give you the short answer. So the first one, are spectra a good tool for studying climate variability? So I would claim, of course, yes. The answer to that is yes. And that even if you're just not interested in studying future climates or simulating future climates, you just want to study the variability in the climate system, should we be looking at spectra more? I would say absolutely. Do we need to talk more carefully about in public discussions about climate variability? I would say the answer to that is absolutely yes, that we should not be giving this vague impression that variability will certainly be bigger in the future. It's not clear at all that that will be the case, and we need to be honest about that. And then a final point that has nothing to do directly with this talk, but I say it whenever I can because I think it's so important, is I'm actually quite skeptical that we can ever really do the things we want to do using deterministic climate models. So CCSM3 and basically all the models that are being used to populate the CMIP archive, which is the standard place people look for climate model output, these are purely deterministic models. And I just don't see how they can get climate variability right with purely deterministic models. And maybe that's something that if people at Statmos could hook up with some climate modelers, that we could start to do something about. All right, so that's the end of my talk. So let me just remind you that I think I've talked about some interesting things, but I've also raised a lot of issues that I've thought about, but for which, you know, we need more people who think these things are interesting to get engaged in. And so I hope that one of the reasons that this talk is that it will encourage some people who haven't visited Chicago yet to come here and visit and talk to me and my students and my postdocs. I have 2 new postdocs coming this summer. And that it'll, so the point of these talks is to generate interinstitutional interactions. And I think there's a lot that can be done. I think there's a lot we have to learn from each other. And I hope that we will all do our best to take advantage of it. So thank you. Please, I hope there are some questions, and either get Peter to turn on your mic or type in a question. I'd be happy to talk about things related directly to the talk or things not so related as well.
Okay, thank you, Michael. So the hard thing here, and I always feel bad about an online seminar, is the lack of claps. So I'm going to give you a little clap here, which is proxy for however many we have, 47 people listening at least. So, oh, there's a clap, clap, clap. So let's, oh, there's a clap icon. Great, perfect. So first of all, let's see if we can... if you have any questions, if it's a short question, why don't you write something in the chat box and we can pass that on. Oh, people are just writing clap, clap. What about questions? There's some writing going on.
I also think it'd be fine at this point to ask Peter to turn on your microphone.
Yeah, that's fine too.
Right. So Peter asked about evidence that variability is increasing. So clearly you want to look at the data record for that, and so I haven't directly looked at those papers. My understanding is the evidence is kind of mixed, that there's some suggestions that and I'm sure it depends exactly what time scales you look at and where you look. And so absolutely we should be looking at the data record for changes in variability. The problem is we haven't changed the system that much yet. And so I think it's going to be a long time before the data record is informative enough for us to really say that much about variations at the changing variability at the daily scale or at any time scale. So if people know differently and know of references, I think it'd be great to send those out to everybody. But my understanding from talking to other people and not having searched the literature myself is that there's some equivocation on that issue about what the data record says about changing variability. So if maybe, Peter, if you want to turn on Stefano's mic, we'll see how quickly that works for someone who's almost halfway around the world.
I've enabled your mic, Stefano. You might have to click a yes, you permit.
To Peter's point, that if we're on timescales of 30 years, that just location scale models fit very well. I would say that yes, I would tend to agree with that. But I would still say that you should then I think there is some evidence. Are we supposed to be able to hear Stefano? Is he actually?
It seems like his. There we go.
Okay.
Hello?
Yeah, hi.
Can you hear me now? Hi. So I have a question regarding the, have I interrupted you? I mean, if you want to go ahead, sorry. I mean, you were saying something, so I don't mean to interrupt.
No, please, go ahead.
Okay. So, no, I just have a question. When you discussed the possibilities of essentially the change in spatial dependence in climate model versus reanalysis data. So now, at least in what I've seen is that reanalysis 1, reanalysis 2, and other reanalysis data product actually show a difference in spatial dependence, which is larger than the difference in spatial dependence between the different climate models. So what would you, I would say it's very problematic to define what is the true climate and how would you change the spatial dependence because you really don't have a reference. At least I would say that the reanalysis data product actually don't, I mean, they change a lot, more than actually the model inside an ensemble.
So, okay, so let me, so that's right. So there's a couple of issues there. So reanalysis 1 is a product that goes further back in time, I think, until the late 40s, and it covers the pre-satellite era. So data records over the oceans for so reanalysis 1 doesn't use satellite data, and therefore it's going to have variability over the oceans completely wrong. I'm
not just referring to reanalysis 1. I'm also referring to reanalysis data product like CFSR, like more recent ones, which are from 1979. So I don't think the satellite is really the issue. What you see is, I mean, literally the spatial dependence differs depending on what kind of assimilation algorithm you use.
Okay. Okay. So I had known that you checked that. It's good. It's good that you've looked at that. My feeling would be if we want to work on the spatial problem, we should give up on doing it globally, and we should do it regionally. Okay. And if we look at places where people actually live, so for over the U.S., so there's a data product called Prism that had until recently only had daily data, and people seem to be pretty happy. Sorry, only monthly data, but now there's a daily Prism data set, and people seem to like the monthly Prism data set. I don't know if the daily one's going to stand up to scrutiny as well. And I would tend to use that rather than reanalysis. But of course, those products only exist, over, say, the U.S. and maybe Europe and maybe Japan and a few other places. Right. So you won't be able to do it globally. But I think that would be the place to start and not even try to do the spatial dependence globally because, at least in part, because of the issue you raised. Mm-hmm. Okay, so Catherine, I'll get back to what Peter was asking about, but Catherine is saying that, pointing out that really what the press talks about is more frequent extremes and that's not the same as variability. That's exactly right. But suppose you were not a statistician or a climatologist and you read articles in the newspaper about how droughts and floods and extreme heat waves were going to become more frequent. Don't you think it would be reasonable for that person to conclude that that was a sign that variability was increasing? And it seems to me that I've talked to people who've definitely been surprised when I've told them that's not necessarily the case. So, of course, you can get more, if you're talking about heat waves, you can get more heat waves just by raising the mean, right? I mean, that's obvious. But I don't think it's reasonable to expect the educated layman to understand that distinction. So I think we do need to be more careful about how we talk about things. So Peter Goodtorp was asking about that a location scale family seems to do pretty well for if we're talking about time scales of 30 years. And I think that's probably largely true. I don't believe that would hold over larger time scales with larger changes in the system. But I also think that the checks that people have done, have people actually looked in the data record whether temporal variability, whether temporal dependence has changed. Well, my guess is they're going to have trouble finding much evidence for it because things just haven't changed much yet. But the comparisons that people have been doing have been mostly at comparing marginal distributions. And I'm saying that we need to look at joint distributions, and a really convenient way of looking at joint distributions is by looking at the spectral domain. Because each frequency in the spectral domain is a different linear combination of the observations, and so I think whether or not there's going to be changes in variability.
We had one other question, Laura Zamboni, if I've got the pronunciation right.
She's just identifying herself as the guest, I think.
Yeah, one up above.
Okay. So she's saying that the climate people also think variability is going up is going up. So, yeah. So, and surely for some things it is going up, but I don't think it's going up for everything. And there is some good physical reasons for thinking variability in precipitation will go up, but it's not clear to me why variability in temperature should necessarily go up. And I'm pretty sure that what's the case is that at some locations and some frequencies it will go up, and at other locations and other frequencies it will go down. And that's part of what we need to be looking at and thinking about.
Great. Any other questions?
So I hope this will encourage some of you to think about taking advantage of Statmos. The one thing we have plenty of money for is for people to travel within the network. The other thing we have lots of money for is for students and postdocs who actually want to visit someplace else in the network. We can actually pay your salary then. So, maybe get you an extra month of pay or get you paid over the summer. And so not everybody listening is a member of Statmos. So let me say a little bit about Statmos. The main thing is you can go to the website. Is that still accurate, Peter? Is that the new address?
That's one of them that works. Yes.
One of the ones that actually works. Okay. So it is an NSF supported network that has 3 hubs: North Carolina State, Chicago, and University of Washington, and a lot of nodes, which include a bunch of universities and some government institutions like Argonne. So Laura, you are in fact part of a Statmos institution. So if you wanted to visit NCAR to do something related to Statmos, which is presumably almost anything that you do that would have a statistical component, I could pay your way to go visit NCAR. And I could even probably pay your salary while you were there. Since you are at a Statmos institution. And the goal is to encourage interinstitutional and interdisciplinary interaction in statistical problems related to anything to do with the atmospheric and oceanic sciences. So not just climatology. So just because I was talking about climate issues, that's absolutely not the only thing we're interested in. So we're looking for people with ideas and with ambition who view it that it would be a good thing to talk to a larger set of people about their research or look for new ideas about their research. I think the opportunities are tremendous. From a purely practical point of view, Peter Guttorp and myself and Montse Fuentes,